In the world of automation, timing isn't just a detail, it's the heartbeat of the process. Today we are mastering PLC timers, TON and RTO. Let's dive into the logic that keeps industry moving. In industrial automation, a sensor can easily tell you when a product arrives. But imagine a fast conveyor system. If the next motor starts the exact millisecond a sensor triggers, the sudden high torque start causes mechanical shock, and products inevitably collide. This is where PLC timers step in. They enforce a crucial wait period, allowing systems to stabilize. Let's look at how this logic prevents disaster. Before diving into specific types, let's open up a standard PLC timer block. They all share the same internal architecture. Inside, you'll find two critical data values. The preset, or PREE, is your target time. The accumulator, or ACC, is the current elapsed time. Next are the three status bits. The enable bit, EN, turns blue when the timer receives power. The timer timing bit, TT, glows yellow while actively counting. Finally, the done bit, DN. This green indicator is the payload. It triggers exactly when the accumulator math equals the preset value. Understanding how these five elements interact is the key to mastering industrial timing logic. The timer on delay, or TON, is the most common timer in industrial automation. Its purpose is simple: wait a specific amount of time before turning something on. Let's look at the timing diagram. When the input condition becomes true, the timer begins counting. This is the accumulation phase. Once the accumulated time reaches the preset value, the timer finishes, and the output, or done bit, turns on. But here is the critical rule. The input must remain true for the entire duration. If it drops early, the timer instantly resets to 0. Now let's translate this concept into actual code. Here is a standard ladder logic implementation for a TON instruction. On the first rung, we have our input condition. Let's call it switch A. When switch A closes, power flows to the TON block. Inside the block, the preset value is set to 5,000 milliseconds. The accumulator, or ACC, begins counting up from 0. Once the accumulator reaches 5,000, the timer finishes. At this exact moment, the done bit, or DN, becomes true. This DN bit then closes the circuit on the second rung to start our motor. If switch A opens early, the timer instantly resets. Now let's look at the exact opposite, the TOF, or timer off delay. Imagine a heavy industrial motor that generates a lot of heat. When you turn the motor off, you can't stop the cooling fan immediately. The fan needs to keep running to cool the system down. This is where the TOF instruction comes in. It is triggered by a falling edge, the exact moment the input signal goes from true to false. While the input is true, the output is true. But when the input drops, the TOF keeps the output active for a preset time before shutting it off. Simply put, a TOF timer delays the turning off of an output. Let's look at the ladder logic for a TOF, or timer off delay. We'll use our cooling fan example with a 30-second preset. Unlike the TON timer, the moment the input condition goes true, like turning on a machine, the TOF's done bit, or DN bit, immediately turns on. The crucial difference happens when the input turns off. This is called the falling edge. The timer only starts counting when power is removed. As the accumulator counts up to the 30-second preset, the DN bit stays true, keeping our cooling fan running. Once the accumulator reaches the preset, the DN bit finally drops to false, shutting the fan off. It keeps running after the stop command. Now, let's look at the third major timer type, the retentive timer on, or RTO. Unlike the TON or TOF, which reset to 0 when their input conditions go false, the RTO has a built-in memory. Think of it like an hourglass. If you lay it on its side, the time stops accumulating, stand it back up, and it resumes exactly where it left off. In an industrial setting, imagine a machine that requires maintenance after 100 hours of operation. Even if the machine is turned off every night, the RTO accumulates the total runtime without losing a single second of its progress. We've seen that an RTO timer holds its accumulated value even when power is lost. But how do you start the cycle over once maintenance is complete? Because the RTO retains its memory, it will never reset on its own. To clear the accumulator, you must program a dedicated reset, or RS, instruction. Let's look at the complete life cycle. The timer runs, pauses when the input drops, resumes when it returns, and finally reaches its preset to trigger the done bit. Only when a separate input triggers the RAS instruction will the accumulator instantly drop back to zero, allowing the machine to run again. Forgetting this reset rung is the #1 mistake beginners make, leaving systems permanently locked out. To truly master PLC timers, we must look under the hood at the PLC scan cycle, the heartbeat of the controller. Every PLC continuously repeats 3 phases: reading physical inputs, executing the logic program, and updating the outputs. Timers are not physical hardware relays. They are software instructions living inside the CPU's memory. During the program scan phase, the CPU's internal microsecond clock evaluates the timer instruction and updates its accumulator value. This means your timer's accuracy is directly tied to the speed and consistency of this continuous scan cycle. To truly master these timers, we need to see them side by side. Let's apply the exact same input pulse to a TON, a TOF, and an RTO. Watch the TON. When the input goes high, it waits. The output only turns on after the preset time is reached, delaying the start. Now look at the TOF. Its output turns on immediately with the input, but when the input drops, it keeps the output running for the preset duration. Finally, the RTO. Notice what happens when the input drops midway. It doesn't reset, it pauses. When the input returns, it resumes counting from where it left off. In summary, TON delays the start, TOF delays the stop, and RTO accumulates total runtime. 3 tools: endless control,